In this lecture number 13, module 2, I am going to calculate deflection at center of this simply supported beam, which is subjected with a point load W at point C, which is the center of this beam. And the length of this beam is L, and from A to C is L by 2, and our objective is to find delta C. And I will be calculating delta C from conjugate beam method. Conjugate beam method. Although deflection calculation can be done by other method like unit load method, moment area method, and strain energy method, but as per my experience, I found this conjugate beam method of this kind of simply supported beam is very easy to calculate, as by generating a conjugate beam of this real beam and finding bending moment at center C of the conjugate beam will give directly the delta C of this real beam. So our main objective is to find first the M diagram for this real beam. Then after that I will calculate M over EI diagram of the real beam. This M over EI diagram of the real beam will be acting as a loading diagram in conjugate beam, and a conjugate beam having a loading diagram, we can easily calculate the bending moment at C of corresponding conjugate beam of this real beam. So let's continue now. Now first, as you know that as I have recommended you to go for any textbook or any good literatures to know about the how we can convert a real beam to a conjugate beam or a imaginary beam. This is the real beam which is our subject of analysis and which is subjected with a point load W at center of this beam. This beam is having a length of L, and this support is designated with A, and this end is with P, and center of this beam is with C. This is a real beam. And corresponding conjugate beam will be, this beam will be of same pattern. This point A, this point is B, length, and there will be a central point C here at this conjugate beam. This is a conjugate beam, and if we are able to calculate bending moment at C of this conjugate beam, then it will give directly deflection at center C of this real beam. So as of now I have formed a conjugate beam of this real beam, but we cannot find the bending moment for this at center of this beam because we are not having a loading diagram for this conjugate beam. So in order to find a loading diagram for this, we need to draw a loading diagram. We need to draw a M over EI diagram of this real beam. Then this M over EI diagram will be directly put on this conjugate beam. After that I will be finding bending moment at center C of this conjugate beam that will give directly deflection at C of this real beam. So now in order to develop M over EI diagram, first I will be developing a moment diagram. Then every coordinate, y coordinate of this M diagram will be divided by with a constant value of EI that will generate a diagram that will call the M over EI diagram. Let's continue with this. This is the real beam. Real beam is subjected with a point load W at center of this beam, and this support is A, this support is B, and center of this beam is designated with C, and load is acting half of distance. Now, in order to draw a bending moment diagram for this real beam, we need to find a bending moment profile. For the profile, we have to find a bending moment at general section XX. You can say x1 because from right of this C and left of this A we have to find bending moment, and this section x-axis is at a distance of x from point B. Now load W, which is a point load, is acting at center of this beam. So from the equilibrium condition of vertical load, sum of Fy will be 0. Therefore, this at point A there will be reaction R1, and at point B there will be support reaction R2. This is the R1, this is R2, and R1 plus R2 will be W. And as we know, this is the symmetrical loading because it is acting at center of this beam. So R1 will be equal to R2. Therefore, it will be twice R1 will be W. This means R1 equal to W by 2 and R2 will be equal to W by 2. Now bending moment at a distance of x from point B will be, we can take a free body diagram from right of section XX, x1. This is the beam which is having a reactive force R2 that I have calculated here, whose value is W by 2, and here is a section XX, x1, which is acting at a distance of x from here, and we're going to find bending moment at section XX, which is called a mxx, mx1. mx1x1. This will be the bending moment at a section XX, x1. Now, as per our assumption, the bending moment, you can say anti-clockwise moment is, this is anti-clockwise moment which is taken as negative as per my assumption. You can take any, you can also take it positive. It's your choice, but I am taking its negative. Now, reactive force R2 is generating a moment with respect to section x1, which is in anti-clockwise direction, and mx1x1 is creating a clockwise moment as I have taken it in clockwise direction. So summation of moment about x1 let's say any point here is D, so you can say x1 or md, summation of moment about point D will be 0 as per the equilibrium condition of moment. Therefore, R2 will be creating anti-clockwise moment, so minus R2 multiplying with this distance x, and this moment is mx1 is in clockwise, so it will be positive. So we can say, and we are taking moment at D, so we will take it as md. So md equal to 0. This means moment at point D will be minus R2. In place of R2 we can put here W by 2 into x. This is the general moment from right of the points, you can say at any section x1 at a distance of x from right of this point C, which is a function of x. So we can say the moment is varying linearly from point here to here, from right of point C. So at x equal to 0, I mean at point B, MB will be equal to putting x equal to 0, it will be 0. At x equal to L by 2, from here we are taking, so we are dealing with at point C. Here x will be L by 2, putting x equal to L by 2 here, so md will mc, because we are going to calculate moment at C, so it will be minus w by 2 into L by 2, it will be minus WL by 4. This is the moment calculated at point C. So we can see here the moment here is at 0, and this at the center of this beam will be WL divided by 4, and it is varying linearly from here to here. And symmetrically, if we are going to take another section x1, x2, x2 here, so we can see here what will be the bending moment profile for that section. Now let's draw. Let's take the same beam. This point is A, this point is B, and this reaction is R1, and reaction at support B will be R2, and load is acting at the center of this beam, which is W, and which is acting at the center of this beam. L by 2, total length is L. Now we are taking a section left of the point C. This point is C. This section will be x2, x2, and x2, x2 is taken at a distance of x from support B, and R2 is W by 2, and R1 is also W by 2, as we have calculated. Therefore, we are taking free body diagram from right of section x to x2. The beam will be here, something like this. There is a point B here having the reactive force R2 equal to W by 2. Here point is C, and there is a section x2 acting here, which is at a distance of x from point B, and we are going to denote this point with point E. This is the point E. Now suppose we will be calculating a moment here. This is a moment that will be mx2 x2, which we can say moment at point E. This is a general moment calculating at a section x2 x2, which is taken from point B at a distance of x from point B. With reference to point B, we are taking section x2 x2, and we are going to calculate moment me at point E, and this will give the general bending moment at a section x2 x2, which will be left of the point C. The entire length of this beam from point C to A will having a profile that will be calculated from this expression. So we are going to derive general expression for bending moment at a section x2 x2. Now, as per the equilibrium condition, summation of moment about E will be 0, and R2 is creating a bending moment which is in anti-clockwise directions here about point E, and ME, as I have supposed, it is acting in clockwise directions. Therefore, and there is a point load which is acting at C, whose value is W, and the distance of this loading is, this is the X, and and from C to B, length of this beam is having L by 2. So this length is X minus, this is X minus L by 2. From C to E, length is X minus L by 2. and so W is creating a clockwise moment. And RB is R2 is generating anti-clockwise moment mx22, or you can say M is also creating a clockwise moment. Therefore, from the equilibrium condition and summation of moment about E will be 0. Therefore, minus R2 multiplying with distance x, and we're taking load W. W is acting at a distance of x minus L by 2, creating a clockwise moment about point E. So we have taken it positive, and it is acting at a distance of x minus L by 2 from point E. So load multiplying with distance will create a moment, and this moment, this ME, which is also in clockwise direction, so ME will be 0. And in place of R2 we can put W by 2, so we can write here ME equal to, right side will be positive, W divided by 2 into x. In place of R2 we have used W by 2 minus Wx minus L by 2. We are analyzing this general bending moment expression from left to the point C. So at x equal to L by 2, we can say at C, MC will be what? At in place of x we will put L by 2. So here we can see MC will be W by 2 into here will be L by 2, and here putting L by 2 it will be 0 minus 0, so overall value will be WL divided by 4. This value is 4. So here bending moment at C will be WL by 4, and same moment has been calculated in right of the any section we have taken at right of point C, which has been marked as x1, and this value general expression has been calculated here. Okay, minus R2 into x plus MD. When it will be coming from left to right, it will be positive. It will be positive. So here MB equal to 0 when x equal to 0, and at C x equal to L by 2. So putting x equal to L by 2, it will be positive from this expression. So it will be WL by 4. Same value. At C, the value is WL by 4, and here WL by 4. Therefore, and now from this general expression, this is the general expression at any section x2, we can find moment at A. At A, you can see x equal to L. Putting x equal to L here, it will give a moment which will be designated as MA, which value will be W divided by 2 into L minus, in place of x we'll put L, so L minus L by 2 will be L by 2, so W into L by 2, here WL by 2 and here WL by 2 will be cancelled, and it will be equal to 0. So moment at A will be 0. So we can summarize here the bending moment at B will be MB will be 0 from this expression which I have calculated here. MB is 0, and MC is here WL by 4. When we have taken right of the any section, which is the general section from right of this point C, which has been calculated as WL by 4, so it will be WL by 4, and from also any section which is the general section taking at left of this point C, which is section x2, the same expression we have calculated WL by 4 at C, so this is right, and at A, as I have calculated here, at A, MA equal to 0, and MA will be 0. So bending moment can be drawn very easily. It is linearly increasing from point 0 to some value WL by 4, and from this it is decreasing to 0. So bending moment diagram will be here. This is the point A, this is point A, this point is B. Here the bending moment is 0, and as per the hinge support, we can say hinge support is having always bending moment 0, and we have proved here it, and is the center C of this beam, and this value is it is increasing from 0 to L by 4. Then again here it comes to point A having a bending moment 0. So this is the bending moment curve having maximum value. This is the maximum value W divided by 4, and which is acting at a length of L by 2 from any support A or B. This is the total length. This is the M diagram. This is M diagram. This is M diagram. Now I am done with M diagram for the real beam. This is the M diagram that I have generated here. The support end is, this is the support end A, this is the support end B, and there is a point C which is the center of this beam, and bending moment is here, this profile, and this value is calculated here, WL by 4, which is called the M diagram, or you can say bending moment diagram. Bending moment diagram. Through this M diagram we are going to generate M over EI diagram. It means every Y coordinate of this M diagram will be divided by a constant value which is called the flexural rigidity, and which is expressed as EI. We are going to divide every Y coordinate with a constant value EI. So as you know, if you are going to divide any curve having this profile, dividing with a constant value will give the same profile, but its value will be somehow lesser than this. So we can draw here M diagram. This is the point A, this point is B, and the center of this beam is C, and here it will be having maximum value of M over EI value. This value will be WL by 4 dividing with EI. WL by 4 dividing with EI will give a maximum value of WL divided by 4 EI. This is the maximum value WL divided by 4 EI, and length of this beam will be having same, and C is at a length of L by 2. This is the M over EI diagram. As per the condition of conjugate beam method, as you know, this M over EI diagram will be putting on the conjugate beam to make its loading diagram. Here as I have told you in the beginning of this lecture, this is the conjugate beam, but we have not yet found out its loading diagram. Now as I have done with the M over EI diagram, this M over EI diagram will be directly putting on this conjugate beam to make its loading diagram. So the final final conjugate beam will be having loading diagram will be here, something like this. This is support A, support B, this is support A, this is support B, and there is a point C which is the center of this beam, and this is the M over EI diagram. It will be directly put on this beam to make its loading diagram. So it will be having a loading diagram of this pattern. This is the final conjugate beam having the loading diagram, and maximum loading diagram value will be here. This is the M over EI diagram value is WL divided by 4EI. WL divided by 4EI. The span of this beam is L and it is L by 2. Here we are having all these things, length of this beam, which is, and this is the symmetrical loading, which is triangular loading is acting over this conjugate beam. So we can find a bending moment at C of this conjugate beam. This is the conjugate beam, final conjugate beam with loading diagram. And by calculating bending moment at C of this conjugate beam, we can find deflection delta C here. So MC, you can say bending moment at C at conjugate beam will be delta C in real beam. So it's our objective is to find MC, bending moment at C of this conjugate beam. So now let's move. The conjugate beam which we have found here with the complete loading diagram. This is support A here, this support A, this support B. There is a point C which is having a value. This value is WL divided by 4EI, maximum value, and this is subjected with a triangular loading of this pattern. So here we need to find MC, bending moment at C will be what? Now in order to find MC, we need to find reactive force at A and reactive force at B of this conjugate beam. So this is the length of this beam here, this is the length of this beam. This is a triangular loading having base and base length L and height WL divided by 4EI. So, and loading is symmetrical about point C. Here you can see left of this point C and right of this point C will having a symmetrical loading pattern. So RA plus RB will be equal to area of this loading diagram will give the total vertical force. So we can say half into base length L into height is WL by 4EI. You can say WL square divided by 8EI. Total load is acting here, RA plus RB. But loading pattern is symmetrical about point C, either left or right. So we can say RA equal to RB. Therefore you can write here twice RA will be WL square divided by 8EI. Therefore RA will be equal to WL square divided by 16EI, and similarly RB will be equal to WL square by 16EI. I am done with the calculation of reactive force RA and RB, which is of same value WL square divided by 16EI. Now we want to find the bending moment at C of this conjugate beam, and it can be calculated here. Now beam is here is RA, since this point is A, this point is B, and this point is C. This value is given as WL divided by 4EI, and RA equal to, as we calculated here, WL square divided by 16EI. So we will be putting here WL square divided by 16EI, and in place of here the reactive force RB will be WL square divided by 16EI, and here is the loading diagram which is acting on this conjugate beam having maximum value WL is WL divided by 4 EI. So in order to find bending moment at C, we will take a free body diagram of this. So taking a free body diagram at a section at C, which will be right of this point C, and which can be shown here separating out a free body diagrams. Free body diagram will be here. Here the point will be C, this point will be C, this point will be B, and this value is WL divided by 4 EI. WL divided by 4 EI, and which is subjected with loading. And you can see loading is acting here. The free body diagram, and this is having a reactive force RB acting here. WL square divided by 16 EI, and this length is L by 2, and we can see here reactive force RB is creating a bending moment about C, which is in anti-clockwise direction. This triangular loading which is acting at a length of L by 2 from C to B, which will be creating a clockwise moment, and our objective is to find the bending moment which is our object of analysis, which will be acting here. That will be the bending moment at C, which I have assumed in clockwise direction. So we need to find MC, bending moment C, from the equilibrium conditions. From equilibrium condition of moment, summation of all moment about point C will be 0. So this reactive force RB will be creating anti-clockwise moment, so it will be negative. So minus RB into this length is L by 2, and this is the triangular loading, which will be the total load will be the area of this triangular loading. So and it will be acting at the centroid of this triangular loading, and this is the total load. Total load will be the area of this triangular loading. So total load will be half this length is L by 2 into WL divided by 4 EI. It will be WL square divided by 16 EI. This is the total load. WL square divided by 16 EI. This is the total load which is acting at a distance of here from C will be 1/3 of this L1, 1/3 of this L by 2. You can take it L by 6. The distance will be, total load will be acting at a distance of L by 6 from point C, 1/3 of L by 2, which will be acting at this point. You can say this is the total load which will be acting at a length of 1/3 of this L by 2, which value is L by 6, and this total load is this one. Total load multiplying with this centroid of this loading will give a moment which will be in clockwise direction. So here we can write total load is WL square divided by 16 EI. So plus WL square divided by 16 EI multiplying with this centroidal distance of the loading diagram, triangular loading, it will be L by 6, and this is the MC which I have assumed, which will be in positive direction, which will be positive as MC we have taken in clockwise direction. This will be the 0. This is the expression for summation of all moment about point C. So in place of RB, we can write here this RB value W square by 16 EI. So we can write here WL square divided by 16 EI. This is the value of RB. RB equal to WL square divided by 16 EI. And here directly putting here this value L by 2. And here we can take a WL cube. divided by 96 EI plus MC will be equal to 0. Now we can rewrite this one here. MC value will be here, going right of this equality sign, it will be having WL cube divided by 32 EI, and it will be with negative sign WL cube divided by 96 EI, and LCM of this one will be 96 EI, so 32 divided by 96 will be 3 WL cube minus WL cube, it will be twice WL cube divided by 96 EI, it will be 2 divided by 96 will be 48, so its value will be WL cube divided by 48 EI. This is the bending moment MC, which is at the center of this conjugate beam. Now we have done with the calculation of bending moment at C of this conjugate beam, and this calculated bending moment is nothing but the deflection calculated center of the real beam. So MC equal to delta C of the real beam, whose value will be WL cube divided by 48 EI. So we can write here that the object of analysis is to find out delta C of this real beam. So delta C will be here WL cube divided by 48 EI. Now I am done with the calculation of deflection at point C of this simply supported beam, which is subjected with a point load. Now I think your all concept regarding the formation of M over EI diagram, and after that calculating bending moment at center of the corresponding conjugate beam of a real beam might have cleared. For any doubt or ambiguity, you can consult me by writing comment in comment box, and I will be surely answer to you. Thanks for watching. Keep sharing to your friends and colleagues.